Hi, and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about latent heat and phase changes. So you will recall from our previous video that I had discussed how adding heat to an object can cause the object's temperature to rise, a point which we will have occasion to revisit and add to in the future when talking about the laws of thermodynamics. But heat usually causes temperature to rise when added to an object and temperature to fall when taken away from the object. With that said, it is possible to add heat to an object without actually having it change temperature. This basically means that instead of changing temperature, the substance changes phase. So in our little recall, we could say something like the heat added to an object is the mass times the specific heat capacity times the temperature change. So now the caveat, or one caveat that we're adding here, is phase changes require energy. So phase changes require energy, and that energy is in the form of heat. So adding heat to a system basically means that you can raise the temperature, but you can also cause a phase change. Specifically, some possible phases. So what are the phases? Phases include, among other things, solid, liquid, gas, and plasma or ion. Maybe we should say ion rather than plasma, but plasma is a valid phase of matter that makes use of ions. Okay, there's other phases as well. There's supercritical fluids, there's Bose-Einstein condensates, etc. But we're just going to focus on these four. So we'll say, and others that are outside the concerns of this particular class. So changing phase, there's different processes for phase change. So processes include, and essentially what can you do? You can melt something. So melting basically means from solid to liquid. And then the opposite of that is fusing. So that would be liquid to solid. Whoops. There's vaporization. So vaporization basically means going from the liquid to the gas phase. Condensation is the opposite. Condensation means going from gas back to liquid. And then there are two other phase changes that maybe we could throw in. There's sublimation. So in sublimation, you go from solid straight to gas. And then on the other hand, there is ionization. So ionization means usually from gas to the ion state. So I'm just going to put e.g. gas to ion. Recombinations would be ions to gases. Now with that said, heat alone is not necessarily how you accomplish ionization, although with sufficient heat ionization will occur. There's actually, for each of these phase changes, some energy associated. So this energy is what's called latent heat. So latent heat is basically energy to cause a phase change, energy which causes phase change without any temperature change. Thus, if you add some latent heat worth of heat to, let's say, a solid ice cube at 0 degrees C, it will melt and become water, also at 0 degrees C. So there's a latent heat associated with this procedure, this process, and that latent heat is basically a heat per unit mass of the object. Now these latent heats are given for different materials, different substances, and they generally speaking are assumed to occur at a given pressure or a given ambient pressure. For example, water, a latent heat of fusion of 334,000 joules per kilogram and a latent heat of vaporization of 2,256,000 joules per kilogram. Now, what do these two things represent? Well, latent heat of fusion, this is latent heat of fusion. Latent heat of fusion represents needed to melt or boil. Melt or fuse. So this is the melt or fuse heat. This is the latent heat of vaporization. So latent heat of vaporization is the heat needed to essentially boil or condense. And these are the only two that are strictly speaking given as latent heats, and to be honest, it makes some sense, which I'll explain in a moment, why there's a latent heat for these two processes. There's also a latent heat of sublimation, although that one's maybe a little harder to discover. And then some materials also have an associated heat of combustion, for what it's worth. Ionization does not have a latent heat per se, but it has something equivalent. And the reason why it doesn't have a latent heat per se is this. If I take water and I boil the water so that it becomes water vapor, and then I cool the vapor, it'll return to being water again. If I take, let's say, nitrogen gas is a gas at room temperature. If I take the nitrogen and I cool it down to, let's say, 60 Kelvin, it will eventually condense to be a liquid. Alright, and then if I allow it to heat back up, it'll be nitrogen gas again. In other words, these processes are reversible. So basically, if I add this much energy, I melt the solid. If I add this much energy, I vaporize or boil the liquid, assuming that it's at its melting point or at its vaporization point, of course. And on the other hand, if I remove this much energy per kilogram or this much per kilogram, then I either fuse or freeze, or else I condense. So it's a reversible process. So these are reversible. If I take energy out and then I put the energy back in, I end in the state that I began with. Ionization, I'm kind of including in this lecture, even though it's not maybe properly part of it. It is a phase change with this distinction. If I take water and I vaporize it, and now I want to go from gaseous water into ions, I won't have ionized water per se. I will almost certainly destroy the chemical bonds in the water so that I have oxygens and hydrogens, and from these I will have removed electrons. So ionization means remove electrons. And you can ionize something once, you can ionize it assuming that it has more than one electron. With hydrogen, you can ionize it once. With helium, you can go twice. With lithium, you can go 3 times, etc. Each additional element you can ionize one more time. It actually takes more energy. The ionization energy is generally associated with your element. It's only really associated with individual elements, and it's associated with those elements for different values depending upon how many times you've already ionized the element. The other difference between this versus latent heat is that with latent heat, like I said, we have a reversible process. With ionization, you do have a reversible process in the sense that, let's say I can take a mole of oxygen and I can ionize everything within that mole one time so that I have a bunch of oxygen atoms, each of which is missing one electron and therefore has a +1 charge, a +1 positive charge essentially. And I can even recombine the electrons with that oxygen and essentially release energy in the form of electromagnetic radiation from those recombinations. But in doing that whole process, if I started out with O2, I don't end with O2. I end with just free radical oxygens. They may now chemically bond, but that's not exactly the same process as just undergoing phase changes. So in this sense, and only in this sense, we might say that this is not exactly a reversible process. If I start with water and I vaporize it, so now I have water vapor, and then I ionize it, and then I allow all the electrons to recombine, I end up not with water vapor again, but with a bunch of oxygen atoms and hydrogen atoms, which may recombine into water vapor, so I may end up with some H2O. But some of the hydrogens will simply recombine with other hydrogens, giving me H2s, and some of the oxygens will recombine with other oxygens, giving me O2s or even O3s, that is ozone. So that process is not necessarily reversible as the other two processes, melting versus freezing, vaporizing versus condensing, are reversible. Okay, how much energy does it take to ionize a material? Well, like I said, it depends upon the atom that you're trying to ionize, or depends upon the element you're trying to ionize. You can look these up, but I'll give a few examples. Okay, hydrogen has an ionization energy of about 1.31 times 10 to the 3 kilojoules. So that's 1.31 times 10 to the 6 joules per mole. For oxygen, it's also about 1.31. It's 1.314 as opposed to 1.312 for hydrogen. So it's a little bit higher, times 10 to the 6 joules per mole. Helium is actually quite a bit higher than is hydrogen. This one is more like 2.372 times 10 to the 6 joules per mole. Neon, okay, so neon, Ne, has an ionization energy of about 2.081 times 10 to the 6 joules per mole. Now you may have noticed that I kind of changed my units here. In the previous set of energies, the latent heats, it was always in joules per kilogram. Now I'm doing joules per mole. So what does that look like in joules per kilogram? Well, you got to look up the molar mass for each of these things. They're not all going to convert to the same conversion factor. For example, hydrogen has about 1 gram per this is about 1.3, let's just round it to 2 sig-figs, 1.3 times 10 to the 9 joules per kilogram. Oxygen, on the other hand, is 16 grams per mole. So our conversion factor is a factor of 10 to the 3. So we have 1,000 divided by 16. So we would have to divide this number by 16, so whatever that comes out to, and then multiply by 1,000. This comes to about 8.1 times 10 to the 8 joules per kilogram. Substantially less than hydrogen when we've converted it over to joules per kilogram. Helium is about a factor of 4 times more massive, so it's actually also less than hydrogen in terms of joules per kilogram, but more in terms of joules per mole. Now, which of the two is the better? Which of the two is the better way to compare these things? Well, if we're trying to compare to latent heat, then maybe we would want to convert over to kilograms. But the reason why we start off by converting into joules per mole instead is because remember that a mole has an exact number of particles present. So in some sense what we're saying is how many joules per that many electrons does it take to remove exactly that many electrons from the collective gas. So these are really more nearly an apples to apples comparison with each other, and really in some sense ionization energy really belongs in a different category than latent heat. Now we can close with a brief example. The example just simply asks how much energy is needed, or how much heat is needed to melt 250 grams of ice at 0 degrees C so that you end up with 250 grams of water at 0 degrees C. So the answer is that the heat that you have to add is the latent heat of, in this case, fusion times the mass. So recall that I specified for latent heat that for water is about 334 times 10 to the 3 joules. So this is 334 times 10 to the 3 joules times the mass, which is 0.25 grams. This is 0.25 kilograms. This is joules per kilogram, which is why we need to convert the units. So 334 times 0.25 is 83.5. So this is roughly 83.5 times 10 to the 3 joules. And that's roughly how much heat you'd have to add to the ice to get it to all melt and end up as water at the same temperature. Alright, that's all that I'm going to do in today's video. Thanks for watching, and I hope you've learned something from it.